In this video, we will introduce the applicable standards for temperature rise. The temperature rise of a switchgear cabinet refers to the maximum temperature increase at the copper busbar connections and key points within the cabinet when under continuous operating current over a long period of time. It is expressed as the difference between the maximum temperature and the ambient temperature, measured in Kelvin K. Specifically, 1 Kelvin K is equivalent to minus 272.15 degrees Celsius, and 2 Kelvin K is equivalent to minus 271.15 degrees Celsius. In practice, the scale of Kelvin and Celsius is the same, but they have different reference points. Therefore, Kelvin K is used as the unit of measurement for relative temperature rise. The baseline ambient temperature for the temperature rise of a switchgear cabinet is 40 degrees Celsius, and the allowable temperature rise is 70 K. This means the maximum temperature inside the cabinet is 110 degrees Celsius. Here is a brief explanation that the temperature rise of a circuit breaker is not equivalent to the temperature rise of a switchgear cabinet. The test temperature rise of a circuit breaker cannot be used as a basis for the temperature rise design of a switchgear cabinet. The main source of temperature rise is components with high heat generation, such as circuit breakers. The structure of the switchgear cabinet determines the position of the circuit breaker. In areas such as circuit breaker compartments where limited components are densely packed, there are also primary contact terminals, connecting joints, and other structures with relatively large contact resistance. Therefore, the temperature rise in and around the circuit breaker compartment is generally higher. Compared to the enclosed design of the switchgear cabinet, the temperature rise test of the circuit breaker is carried out in an open-air environment, and the test results can only be used as a reference basis for the design and testing of the switchgear cabinet. A good design should be that the vertical bus bar is installed onto the circuit breaker terminal through the extension bar, and then vertically upward. This design can dissipate heat through the extension bar, conduct heat to the space behind the circuit breaker, and form an upward heat channel to create a convection effect that carries the heat out. In the design of withdrawable switchgear cabinets like center-mounted cabinets, some designs save on copper bars by hanging current transformers under the bus bar chamber. The copper bars coming out of the contact box are directly connected to the current transformers, making it difficult to effectively dissipate heat from the connection points inside the contact box. However, if the current transformers are arranged at the rear of the compartment and connected to the contact box and current transformers through extended copper bars, these bars can effectively conduct heat out. This design has a significant effect on temperature rise, especially for high-current switchgear cabinets. The temperature rise of fuse holders, especially those in enclosed ring main units, is significant. Fuses typically have a maximum rated current of 125 A, and therefore the design of fuse holders and conductor cross-sectional areas is generally economical. However, this design considers the current carrying capacity, but ignores the enclosed environmental factors that prevent the heat generated by the fuse holders from dissipating, which can pose safety hazards in long-term operation. Equipment manufacturers should design larger fuse holders and external connection buses to ensure reliable connections while dissipating the heat generated by the fuses. The above is a popular science introduction brought to you by Hertzmann, Hangzhou Power Technology Company, Limited. Welcome to our official website, www.hertzmannpower.com. Thank you for watching.